because of you see that might have driven you to here. So similarly, somebody else may help maybe. Okay. Some of the
Exactly.
videos I could not able to even record it because that time we had a problem. Otherwise, we had discussion. I had discussion with several people. We could not able to get the recordings and all that stuff. So that's why most of the things still are open. So I will try to put some videos on that. No problem.
All right, sir.
Yeah, yeah.
Thank you, sir.
Please. Yeah,
Uh,
yeah. Shall we go to the question now? Yeah.
okay. Please let me open the file first so I can share my screen.
Yeah, please.
Sorry, this is not opening.
Yeah.
Sorry, sir. Hold on, sir. Let me come in. It's opening.
Yeah.
Why is not happening? Oh, okay. So, sir, you can record maybe when you publish, you can share the link to me too. I can try to follow from there.
Yeah.
Actually, I'm sharing my screen. Okay.
Yeah. Not yet come, but yeah, it's coming now. Yes. Yeah. What's your question?
Okay, sir. Thank you again for this time
No
and this
problem.
opportunity, sir.
No problem.
So
No problem.
actually, I just started doing research in this area. So I'm
Okay.
actually looking to understand more principles how reflectarray unit cell works, especially
Yeah.
for design, uh,
Mm-hmm.
how to analyze the result, something like that. Maybe that would be
Okay.
the first question.
Yeah.
Actually, this cell, I designed it from this paper.
Okay.
Maybe I'm going to share the paper first.
Yeah.
No, this. Yeah, this is the paper
Okay.
that I'm really using to design this unit cell. I
Okay.
I already fold all um I already fold all details,
Yeah.
but
Okay.
actually there is no information mentioned about the cell dimension from here to here. They didn't know to give some information, but I tried to use some optimization method to play on the
Okay.
subtract width if I can find something similar. But actually, I did not really get the similar information.
Okay.
So my first
In
question
general, you
is,
see, thumb rule is, most of the time they take is lambda by 2, okay, of the design frequency.
okay, is lambda by 2?
Yeah, most of the time. So 99%, basically.
Oh,
Yeah, yeah,
oh, that's really good. So my first question is,
yeah.
the Z max 1. This is for XY polarization, and the Z
Yes, yes.
max 2 is for X polarization. Is it that true?
Exactly. So one for horizontal, one for if you are exciting two modes, then one for
Okay.
vertical, another one for horizontal. Okay. So here the max is for the port one ideally S11 like that. Okay. S max means SZ max means it is S11. If it is SZ min means S22 like that. Okay. Port number 2. That way we have to correlate.
Okay. Oh, okay. That's very
Yeah,
good.
if you are having two ports, no, you will have this Z max max, SZ max, SZ max like that, and SZ min. Okay. If you are having single port, then it will automatically collect SZ max, SZ max. That's all. So that is for Z max means so wherever max is coming, which is first port. Okay, you have to assume it as one. So first one, whatever you have selected, right, it is S11. Okay, of the port one.
Okay.
Of the mode one.
Okay.
Okay. Bracket
Okay.
is mode, basically. Bracket is mode, whatever you are having. Z max bracket 1 is there, right? That is mode, okay, which is basically vertical. And then next mode 2 is horizontal, okay. And here max is nothing, corresponds to 1, okay. And min is corresponds to, Z min is correspond to 2. So here, whatever you are showing here on the right, you can see Z max of 1, Z max of 1, which is S11, okay.
Okay. Okay.
So
Oh,
how
that's
I am
very good.
saying, yeah, can you go to ports on the left? Ports,
The port.
ports, yes, yes. Here
Yes.
you can see, can you click on the Z max? Can you close this result? Yeah, yeah, cancel this.
Cancel this, right?
Yeah, 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 yeah. So where is it visible? It's not visible actually.
Uh,
Okay, Z min? Can you press Z min?
okay.
Oh, it is there. It is there. Okay, okay. Can you zoom out a bit so that we can view both the ports?
Okay. Zoom out.
Yeah, or else that there is four arrows are there, right? That button you can press
Zoom out the
on the
unit cell,
bottom.
right?
No, no, no. On the,
Here.
there's four arrows will be there on the bottom, on the bottom, on the bottom of the tool.
Okay.
Or 1 minute, 1 minute. There pan is there, right? Actually, it is reset
Uh, I,
to
I
that
don't
tab view. Yeah, reset. Yeah,
view. Oh, where is
view.
view? Here, right? Here. Yes, sir.
Reset.
Here, reset view.
Hello.
Yes, sir.
Hello.
Yes, sir. Is it this one?
Yeah. So reset view. Reset view. There is an option, right? Yeah, yeah.
Yeah,
Reset view on the right.
this
Yes,
one.
exactly. Yeah, yeah, that one. Okay. So now Z max. Can you click on the Z max? It will be in other side. Can you go to click on the reset view? Reset view. Yeah, it is on the other direction, right? That is
Okay.
the one. Okay.
So if I click like this, I can see both of them. Oh no.
Yes. No, no. Can you click on the ports? Can you click on the ports itself? Ports. Yeah. You can see both of them. Oh, or else you have to select manually too.
Okay.
Can you select Z max and Z control? Press control.
Yeah, is the
Press.
control is not really working
Okay.
for
Okay.
them,
It's okay. It's okay. No
but
problem.
I
Okay.
can see all of them. Oh, that's very good.
Yeah.
So,
Yeah.
sir, how to verify that the unit cell width is like lambda by 2?
Lambda by 2, see, for example, you are design frequencies, for example, 10 gig, okay, 10
Yes.
gigahertz, okay.
Yes.
So, what is the lambda? It is 30 mm, okay. Then lambda
Yes.
by 2 is that 15 mm, okay. So, approximately you can take 15 mm and then do your design, okay. If you want to operate in middle frequency or design frequency is 10 gigahertz, then you can use that as the lambda by 2, okay.
Okay. Okay.
Yeah. Most of the time, maybe I suspect that that paper could have that because that's why they could not able to, he could not have mentioned that. Okay. So
Okay.
ideally speaking, the design frequency, if you know, then you can just take a lambda by 2 and then start working on that paper basically. If they have not
Okay.
given explicitly.
Okay. Is there some
Is there
some
anywhere
design
0.5 lambda
under?
or 0.7 lambda like that they have mentioned? Can you go to that paper so that I can tell you?
Okay.
Can you go to that paper? Yeah.
Yes.
Yeah, any lambda naught, something like that, it is there for unit cell design.
Unit cell design.
Yeah.
I think should be here down. Unit cell design. I think
Not this
this.
one. Ah, yeah, yes, yes, yes. When wait. Last tangent. Okay, everything is given. Then Okay. Can you go up, please?
Where here?
No, just up. Go up, please.
The top?
Yeah. Go to that. Go up, please. The PX, PY. What is PX and PY?
The PX, PY is the patch size.
Patch size. Okay.
Yes.
So unit cell size, anywhere they might have mentioned it as a lambda naught or something like that. Point
They
five
did.
lambda naught. Grass point lambda naught. They might not have mentioned the dimension, but lambda naught something like that might be there.
I've seen in this one. I don't know with relatively large aperture of size of less than.
Greater than 20 wavelength. That's okay. Yeah, 20 wavelengths. Yes.
Is it this one?
20 wavelengths means, yeah, not this one. This is for array, aperture size,
Yes.
metasurface aperture size. Okay, for array. Okay. So maybe somewhere they might have mentioned. Can you search for wavelength?
Okay.
No. The spelling is incorrect. WAVENGTH. Yes. LEN
And
GTH. GTH.
DT. Oh yeah. DTH.
Can you search for it? Can you search for the one? Next. Quarter wavelength metro stripper. Next.
It's
Quarter
not.
wavelength stub.
This is.
That's all, right? Okay. Fine.
Yeah.
Okay. So what they are saying, so the length of the stub is the right stub with the patch. That is quarter wavelength, which means lambda by 4. Okay?
Under by 4. Okay.
Yeah. Okay. So one more thing, I do you understand this equation on the bottom? That equations, the array factor equations on the bottom. Can you come down, please?
Okay. Yes.
Come down, please. Yeah, here. You understand the equations? It's nothing related to that, but it's a array factor basically. They have
Yes.
mentioned it's basically array pattern multiplication they have done. Okay. So do you
Okay.
understand this, or or should I want to explain you these things?
So if you can explain it, it's gonna be fine.
Yeah, definitely. Okay. So shall I ask for request control?
Contour.
Yeah, control. I will
Okay.
request your control. Can you grant me a control so that I can explain you?
Okay. Sure.
Yeah. Okay. So can you zoom a bit? This one.
Hello, sir.
Yeah. Can you hear me?
Oh, to zoom out.
Yeah. Please.
Okay.
I don't know. Internet is on and off. It's not coming. Okay. That's
Yes.
fine. Okay. So, okay. Fine. Yeah, it's visible now. Yeah. Okay. Okay. First of all, they might have mentioned this equation for the how to find out the phase to be compensated like that, right?
Yes.
1 second. Let me check. that equation is there, then it's fine. Otherwise, we'll start with this. So here it is there, right? Okay, okay.
Yes, that is right.
This is for the 155.8 mm. Is 4.9 mm. Okay. So what is the substrate?
Substrate height is 1.58.
Okay, height is 1.58. That's fine, but px and py maybe that may be the unit cell size. So what is the frequency they are designing now? This one?
I think it's 7 something like that. Design frequency is
Okay,
7 point something. Yeah, to check.
okay. Then I think lambda by 2 should hold good, actually, basically. Okay, let's see. Okay, so let me explain this video, this equation first, and then we can move on to that. So you can search
Okay.
for that lambda. So maybe they might have mentioned lambda somewhere. Okay, or you can start with the lambda by 2, and then unit cell size. That patch size we can mention it as this one, 5.8 mm and 4.9 mm. It's okay.
Okay.
Yeah. So then let me 1 minute. Let me go to that. Okay. So here what they are here what they are mentioning it is like if E of theta comma phi. So theta
Yes.
comma phi means do you have a paint is open? Paint. Can you
A
open the
paint.
paint?
Okay.
Paint. Yeah.
Okay. I can open, sir. Oh, the computer is the internet has problem.
Yeah.
Oh yeah.
Uh,
Okay.
it's not showing here. Can you drag? Yeah. Okay. That's great. Okay. Thank you so much.
Welcome, sir.
Okay. So here you can see that in array pattern, right? You will
Yes.
have a yeah, see array factor, sorry, a pattern multiplication. How it will happen? You will have array factor multiplied by element pattern, right?
Yes.
Element pattern. So here element pattern is this one. Okay. So this is the element pattern basically.
Okay.
Basically this is the element pattern. Then you are having an array factor like this. Okay. This one is array factor. So here actually gamma mn means, see why they are including this gamma mn. So this will include the matching basically. So matching in the losses that incur this in this due to the matching and all that stuff. So here we can see a reflection amplitude and phase. Sorry, reflection amplitude and phase. Because in order to account for matching in the pattern basically. Okay. So
Okay.
ideally, if you have a ideal pattern matching, so 100% matching means you are delivering the power to the array element. It is up to the
Yes.
element to radiate or not radiate. That is okay. Okay. So and
Okay.
you can see here that here this equation, right? So
Yes.
fmn of theta comma phi, that is this scattering pattern. So or we can say array factor kind of thing. So here this is the kind of a projection. So basically this equation tells you that, so you have a array means you will have a x1 y direction, correct? So you will have so many elements in the x and y direction, right? For example, let's say 4 cross 4 array. Let's take 4 cross 4 array. So in 4 cross
Okay.
4 array, so we will distribute the array element, right, with a lambda by 2 spacing. For example, lambda by 2 spacing. So each element will be in one position. If it is a rectangular array, you will have a 4 element in the horizontal x direction, 4 element in the y direction. So 4 cross 4 will be there. Okay. Actually, 4 cross
Okay.
4. So here, so M means, so along X, how many elements? For example, let's say zeroth element, first element, second element, third element, like that. Okay. And the
Yes.
second is dx is nothing but your along x, what spacing you are going to give. Is it is lambda by 2 or lambda by 4? It's up to you to decide. Depends upon the beam width and gain that you are expecting. Okay. Next is
Okay.
sin theta cos phi. Why we are putting? Because we are playing with the CBR. It's not in one single line, right? It is going to be a 2D plane, correct? So we have
Okay.
to mention in terms of spherical coordinates, basically, or rectangular coordinates, which is mentioned. We see any rectangular point, right? Rectangular coordinate point we can mention in terms of sin theta cos phi, right? So because you have a theta value that is there, and the it's actually basically a three-dimensional. Can you go bring back that paint, please?
Okay.
Yeah. Okay. Okay. Oh, yeah. So here, see, let's see. See. Okay. So now
Yes.
you have four elements, right? Let's say uh, like this. Sorry, it
Yeah.
should be a equal element, but somehow it is taking like that. Okay.
It's okay, sir.
So,
It's okay.
so here it is. See, this is, let's say, this is the x-axis. Oh,
Yes.
sorry.
4x4 element.
This is x-axis.
Yes.
This is y-axis.
Y-axis.
Y-axis. Okay. So
Okay.
now this is z-axis.
Yes.
Z-axis, right? Now I have to see the effect of means the radiation pattern, the radiation that is happening, element pattern basically. So element that is radiating from here in this position, right? So now I
Yes.
have see with respect to YZ and XZ, we call theta, right? Theta.
Yes. Theta. Yes.
Between XY, we call it as phi, correct?
Yes. Yes.
Yeah.
Fine.
So now you have to project. So for example, theta is, let's say, I need to capture the pattern, radiation pattern with respect to theta 30. What is the radiation pattern? With respect to theta 90 means which will fall on the XY plane itself, right? So what
Yes.
is the radiation pattern? So radiation pattern is actually what? It is a power distribution. That's all. So distribution of power in the respective direction. That's all. It can be a, how we can ensure. So we can mention only with the sin theta cos phi. That's all. Sin theta cos phi, because it will, how it will come. For example, let's say this point I have to measure. So now what I will do? What is theta over here? Sorry, what is the phi over here? There will be a phi. If I want to measure this point, I have to take the this spacing between the elements, and then you have to then first you will calculate in terms of cos phi. Then what you will do, projection on the this theta to this plane with respect to the you are seeing this plane from means out of the boat, right? So which
Yes.
with respect to theta, where is that? That's why they mention it as sin theta cos phi. Next is n dy sin theta sin phi. Sin phi, just it's just because x and y are 90-degree phase shift, 90-degree line, right? So therefore cos phi will become sin phi. That's all. So here, this is the this is for the, for example, this gamma n EFI n is mn is nothing but your, basically the gamma mn is your amplitude, reflection amplitude basically. Okay, what you will
Okay.
get for the SZ max of 1, Z max of 1 is that, right? For example, so SZ max of 1, SZ max of 1, 1, okay, then Z max of 1. It will have two components. So let me show you in the CST file itself.
Yes.
So here only result is that. So this is the one, right? It has,
Yes.
this is amplitude basically. Okay. So amplitude in
Yes.
dB. If you want to see in linear, you can see in the linear. Then if you want to see the phase, right? You can see
Yes.
over here phase. Okay. Here
Yes.
actually now the latest CST tool are having wrapping, unwrapping like that. If you go
Yes.
to plot properties, you will see raw file, raw data, unwrap. You can see here
Okay.
like that. If you apply, it will become, say, it will be unwrapped one. If you want to wrap between, 182 minus 180, it will, wrap between minus 180 to plus 180. That's it. So if you want to
Yes.
wrap between 0 to 360, it will wrap, because it's a kind of, I have explained in some of the videos that how to
Yes,
wrap
yes,
these
I've seen
things.
in this.
Okay,
Yeah,
those
I've seen in
things.
this. Yeah.
Okay. So now this is this one, like what we call it as uh, you know uh, where is that file?
Yeah, that's one. The third one. Yes.
This one, right? Okay.
Yes.
So now so this is the, see, this is the amplitude and phase. Okay. So why
Yes.
we are concerned about these things? Because see, let me show you. Okay. So why we are concerned about this is, see, you are having some feed over here. This is the metasurface or reflectarray, whatever it may be. Okay. So the
Yes.
signal is coming over here and gets reflected.
Exactly.
Okay. So now, if my reflection coefficient is, actually ideally it should be 100%, which means what? It should be 0 dB.
0 dB. Yes.
I need 100% reflection. Okay. So if
Yes.
there is any loss, that I have to account, right? That I am doing with this gamma mn. For example, I am having 10% loss, or in terms of dB, we can say 1 dB, 2 dB, or 3 dB. But it will not be acceptable. Maybe 0.5 dB to, I see, zero point 0.3 to zero point 0.5 dB, they will accept, basically. Okay. So loss will
Yes.
be there. And also phase. Phase is also very important, because it's a complex number. So whenever wave hit on this wave, then it reflect back, right? So
Yes.
ideally, in the behind the feed or whatever it may be. So if you want to see the wavefront, on the wavefront, you should have a uniform phase. That is the idea, right? If you are having
Yes.
a non-uniform phase, then what will happen? So you will not get the planar waves, basically. There will be something like this, some kind of oscillation will be there, right? So that's why
Okay.
the phase is also very important. Okay.
Very
The
important.
phase, how it is introduced, if you want to dig into that, for example, unit cell has, you can see that there is a substrate, there is a patch, and there is a ground plane. Okay.
Yes. Yes.
There is a ground plane. Okay. So here, see, the wave is till this point, it is coming in free space. The moment it enters to this patch antenna, okay. So patch antenna, we can consider it as artificial dielectric, because if you have a planar dielectric, no, it will have a almost, if you see, if it is a homogeneous substrate. So the moment the wave is coming in free space, the moment it enters, there will be a decay in wavelength. For example, lambda will become lambda g. Okay. So how we calculate lambda g? It will be lambda naught divided by square root of epsilon r, basically.
Yes.
Okay. Square root of
Yes.
epsilon. So what will happen? So velocity will go down, or we can say will go down by this value. Okay, epsilon r,
Yes.
because it depends upon the medium density of the medium or dielectric constant of the medium. The velocity will go down. Okay, so here
Yeah.
what we are doing is, if you just print some patch antenna here, that is called as, we call it as artificial dielectric, right? Or
Yes.
metamaterial. Many things are there. So where what we are doing by, printing the some form of a metallic structure, or we are complementing this, we can able to control the overall dielectric constant, effective dielectric constant of the substrate, right? Correct? Or
Okay.
we can say the whole module. That is
Your
the
mod.
fundamental principle for the artificial dielectric, or else, or as well as this one. What do you call it as metamaterial or anything? Okay. So here, what will happen is, see, the moment it is enters to the patch, so what's happening? It is entered into the complex medium, basically. Okay, it's
Yes.
basically artificial dielectric. You can call it as artificial dielectric also, because a substrate will behave. See, if it is alone, it will behave one fashion. If it is,
Mm-hmm.
it is printed with some patch, okay, of different shapes, it will behave in
Yes.
different manner. Okay, the effective dielectric constant will become different, right? So
Yes.
what is happening? The wave is getting inside. If you're having ground plane, what will happen? It gets reflected, right?
Reflected.
So reflected. So what is happening? So it is traversing so some distance within the substrate, or because of the structure it is following some routes and come over here and come back. So what is experiencing? It is experiencing some kind of phase shifts. Okay, or we can say
Okay.
delay. Okay, or we can say delay. So in time domain we call it as delay, but in complex numbers we call it as phase. Okay, so
First,
time
yes.
delay, we have phase and delay, all are almost interrelated parameters basically. So here what is happening? So the moment enter into the this structure, what is happening? The wave propagation speed is getting changed. Okay, or if you in terms, if you talk in other words, it is delayed or phase shift is introduced in this one. That is why if you want to steer the for example by this characteristic only you can control your radiation characteristics of the overall array basically. This is the
Okay.
fundamental principle. Okay, so what you have to do, you can control by controlling this phase. Okay, by controlling the making a new or like complex, I mean printing structure, new shapes. So you can able to control the phase shift that is introduced by the unit cell. So thereby you can able to control the radiation pattern. Why? Because of this equation. You can see here when you control the phase, I can able to control this addition pattern as well. Overall array pattern basically. Okay, that is the meaning of this. So now we have to summarize. Let me check. This is the basically a radiation pattern. It's a function basically. So theta comma phi. It will be in terms of theta comma phi. Here m dx sin theta cos phi. Why we are mentioning it is in a rectangular coordinate system. Therefore we are having these things. It's basically spherical coordinate system. Next
Okay.
is this gamma mn is to account for the losses incurred in this particular thing, because by the moment it enters into the electric, it will experience some losses because
Yes.
polarized.
Exactly.
Okay, yeah, that losses is accounted over here. Okay, because when you measure the S11, if you are not getting perfect one, or in dB it is 0 dB, which means
Yes.
some loss is there, 0.5 dB water, that we are accounting here. This phase is nothing but your whatever the phase introduced by this one. So I can able to see these are all some of the parameters I can able to control my radiation pattern. Okay, so this is
Awesome.
nothing but your element pattern. So each element will have some pattern, right? For example, approximately, it can be a kind of a broad pattern like this, or some kind of eight pattern like this. Okay.
Okay.
If you are having ground plane on the bottom, then you will have a kind of broad pattern like this. Okay.
Okay.
So
So,
this element. Yeah.
what about this? Is same situation also happen for transmitter array? Is it same
Exact.
or
Exact. Transmit array. What will happen is, see, you will not consider the ground plane. You will just
okay?
cut this. That's all. The
Okay,
wave is
transmitter array does
propagating
not.
through this. Yeah.
Oh,
Okay.
okay. So
Yeah, 1
transmitter
minute.
array doesn't have ground plane.
Yes, exactly.
So it's this
See,
is the
le-
same like FSS.
yes, exactly. So here you can see this is
Yes.
the feed. If it is a reflector array, what will get? You will experience the phase and come over here.
First part.
If it is
Yes.
a transmit array, what will happen? You will not have any ground plane over here, or reflector,
Okay.
ideally reflector. So you are having transparent surface. Therefore, what will happen is this phase will be experienced. It will experience the phase and then collimate the waves like this. That's it.
Okay.
That's
Okay.
both ways it will be same. The equation is same. Only thing
All
is
right.
that, so how you take this element pattern? Here element pattern will be, if it is a transmitter, you will have a element pattern as almost 8 pattern, because it's going to be a dipole, right? Dipole kind of.
Okay.
But if you are considering it as a reflector array, then it will have a pattern like this. So accordingly,
Uh,
this also will vary.
Oh, okay, okay, okay. I got it. I got it. So means that transmitter array is working like FSS, right?
Exactly, exactly.
Okay.
Frequency selective surface. So the thing is, see, ideally, frequency selective surface, metasurface, reflectarray, artificial dielectric, and
Yes.
lenses, artificial lens, all
Yes.
are working in a similar principle only. The way if you are reflecting back, then it will be call it as a reflectarray. If you are transmitting that, then you can call it as frequency selective surface, which is in analog domain basically. If you talk in terms of time domain or phasor one, and then you call it as a for
So,
example if yeah, we can call it as transmit array like that. Okay, so it is
so,
all
so,
boils down to same point only, phase
so
composition.
what is the difference between Metasurface and AMC.
Artificial magnetic conductor, right? Okay.
Yes. What's the difference, sir?
Okay. See, the thing is, see, yeah, metasurface is used for, see, it is used for many purposes, basically. Okay.
Okay.
So how they are designing is, see, the thing is, depends upon the, see, for example, I have this, I have an element over here. Okay.
Yes. Yes.
By controlling this phase, I can, for example, some ray is coming over here. I can steer the beam in this direction, in
Exactly.
this direction by Snell's that one formula is there, right? Refraction,
Yes.
that formula. I think geometric theory of diffraction, something like that. One, one ideal metasurface. No, when you search for metasurface, that one Bible paper will come. There
Yes.
they kind of explained how the velocity and sorry that dielectric constant, there is our refractive index and how it affect this wavelength. So I can able to steer the beam any direction that I want. Okay, it is metasurface. If it is AMC, artificial magnetic conductor, what it does is, see, it's a kind of magnetic conductor. See, it reflect back the signal with a zero phase. That is the idea, basically. In patch
Okay.
antenna, right? In patch antenna, you will have, for example, let's say here, this is the patch antenna. If you are having ground plane like this, okay, you should
Okay.
have, see, let's say, see, um, you should have a lambda by 4 distance between this patch and this ground plane. You cannot have in realistic manner, right? Because for example, lambda by 4 or 10 gigahertz, say what is the value? It is 15 mm. 15 mm thick substrate you cannot have, right? You cannot place
Yes.
this one. So in order to get the in phase component, so what we do is, still we can when a 0.8 mm, 0.5 mm only we use the substrate, right? If you are using
Yes.
artificial magnetic conductor over here, whatever gets reflected over here reflected with a zero phase. Therefore, it constructively enhance the gain of the antenna, basically. So in general, they use for that, and they in some other purpose, what they will do, they in order to suppress something, they use that. So many applications are there.
Oh, all right. Thank you so much, sir. It's really
Right.
clear. Thank you
So
for explaining.
that's why I see AMCs. All I know, see, the thing is the raw concept behind all these terms like AMC, metasurface, all these things. Where it boils down is, for
Yes.
example, see, when how wave propagate within the medium. That's all. Okay, that is the idea. Okay, so the medium, no, what we are doing, we are playing with the dielectric constant only. That's it. Okay, if it is air, we are having dielectric constant of 1. If it is medium, some standard substrate, it can be dielectric constant of 2.2 or whatever it may be. You can control the same substrate with a different. If you want to control the dielectric constant of the substrate, then what you can
Yes.
do, you can print some metallic structure over there with of different surface, for example, cross dipole or anything. Therefore, you can able to control the effective dielectric constant of this medium, so that the you can control the propagation of waves, basically. Okay, epsilon r.
Okay.
Okay, you are trying to manipulate with the help of see, our substrate. No, you cannot do beyond certain level. So what you are doing, you are by printing these structures. So that is where the meta surface came into picture. They call it meta surface is basically a two-dimensional version of meta material, basically. That's why meta surface they call it as. Okay.
Okay. Okay. Okay. Oh,
We were
that's
this. Yeah.
that's amazing, sir. Amazing.
No problem.
It's really useful.
Yeah.
Um. So I'm gonna I'm gonna ask some another question.
Yeah. Please, please. Yeah. Please go ahead.
Yeah.
You
So
can
I
take
think
your.
from
Yeah.
this, yeah, actually, from this part, I really understand. Thank you
Yeah.
for
It's
your time.
okay. No problem. No
Okay.
problem. Welcome.
So
Thanks for reminding me to go back to my PhD work and then remind.
yes,
Yeah.
exactly, exactly. You
Yes.
was
Yes.
helping us, you know. You are you
Yeah.
are
Yeah.
you are very far by helping people out there.
Yeah.
Actually, sir, I want to know. I've seen people making a full array in CST.
Okay.
Means that the way you just design, so giving different size of giving different size of unit cell for
Yes.
the way to control different phases. So
Yes.
actually,
Exactly.
I don't know how to do that, sir. that was my
Yeah,
second.
yeah, okay. So there is, there is one video, one or two videos I have done for that. So how, basically, I will tell you the raw idea, okay? And
Okay.
mm, I want to show you one equation, but I don't know where it is. Let me just show you. 1 minute only.
Okay, sir.
Just a moment. So let
Okay.
me search for it. Mm, So can you please open this page? I have pinged you on chat.
Okay. I should open a chat, right?
Yeah, chat. Open the chat, and then whatever I pinged you, right? Can you open that?
Okay. Let me have control. Yeah.
Second one as well.
Yes. Yes. I've seen this. This one, sir.
Yeah, the second one as well, and third one as well.
Okay.
Can you open that all?
This is on the second one. This is how you open it. There are only two.
Yeah, yeah. Third. I have nothing now just now. Can you go back to chat, please?
Yes, I'm on the chat, sir.
Chat, and the last you can see some link is big link is there. Just click on that.
There is big link for Google.
Yes, exactly. Can you click on that?
This one.
Exactly. Yeah, exactly. This is what I wanted to.
Okay.
Okay, so now, so the thing is, shall I start taking control? Okay, so can you see here on the right? Can you see here?
Yes.
This is the
Exactly.
parabolic factor. Okay, okay.
Yes.
So now I am having a feed. Horn antenna will always radiate in, ideally, assumption is it always radiate in spherical waves, right? Spherical
Yes.
waves. But if you are having flat surface water, if you, parabolic reflector shape itself, it's a kind of spherical waves. Okay, that's why what it does is it is compensating the phase, because the reflector what it does, it just reflect whatever it comes, right? It's a planar
Yes.
reflector. I mean, it's a kind of plain aluminum foil sheet or whatever it may be. Okay, so what it does is, see the shape itself in such a way that it compensate the phase of the incoming signal in a exact manner, correct? Okay, so the spherical waves, see what will happen is, in spherical wave itself you have some part of the signal is coming first, some part of the signal is coming next. So what you are doing, you are compensating by with the help of shape. Okay, but in reflector what is happening is you are having flat surface. Okay, you are having
Yes,
flat
sir.
surface. So how do you accompany these phase changes? This phase, okay? That is what is done by, first is the steps is two steps. One is first we need to find out what phase I need to compensate at each point with the help of parabolic equation, basically. With the help of parabolic equation, okay? So parabolic equation is what it does is in each position of this array, it's a circular array or a square array or a rectangular array, each position of the each location of the element, what phase I have to introduce such that I can get the planar wavefront. That is the idea basically. Okay. Okay. So can you open that second one? Okay. Can come here. Okay. There is a full text was there. Oh, suddenly oh, your son is crying. It's okay. No problem. Can you download this? Can you please download that and open? Hello? Can you please download this and open that file that I
Yes, sir.
can show you?
I'm downloading.
Oh, sorry. Okay.
So I don't know why my Internet Explorer, my download is refusing to download. I'm trying to find out, sir. Please give me a
Okay,
minute.
please. No problem, no problem.
Yes. Don't know why it's not coming. They are saying that your website is blocking. Okay, let me try again.
That one only, right? It is already open. Can you go back to that page?
This one?
Yeah, file. On the bottom. Yeah, this one.
Okay.
Then here also may be there, right?
Yeah, this is the book. I think
Oh,
maybe
okay. Yeah, here also it will be there. Here also it will be there. Can you go back to this is, I think, Payam Nayari book, right?
yes.
Okay, it will be there. This is general introduction.
Yes.
Yes, exactly. This is what I want.
Okay.
Okay. Yeah. So just now I mentioned, right? So
Yeah.
what I have to do is the phase center of the feed horn antenna or feed antenna. Any feed antenna can be anything. It can be a
Yes.
horn, it can be a printed architecture, anything. Okay. So what
Okay.
will happen is, see, first as I explained just now, just before, where is that one? this one. Okay.
Yes.
So here
Yes.
this I have to ensure the phase to be compensated to be met in order to get
Yes.
the spherical waves as I am getting in the parabolic reflector. Okay. So
Okay.
here what I'm doing with the help of for the planar surface itself, I am going to achieve that. So how I am going to achieve? So how I am going to achieve? See, I need to find out the phase to be compensated at each plane, each point basically. Okay. So
Okay.
it's a kind of tricky thing. Okay. So in see here here actually the difference between this actually parabolic reflector and this one is that here we
Yes.
are compensating the phase in discretized manner, whereas in the parabolic reflector we are compensating in a continuous manner. That's it. Okay, that is the only difference. But in parabolic reflector also while analyzing we used to say that it's a discretized into many small modules. Therefore, we are getting. So this is the phase center of the feed horn, or we can say any antenna. Then it is
Yes.
getting reflector over here, and this is the beam direction that we are projecting. Okay. So
Okay.
with respect to theta naught, which direction I'm projecting the beam, or with respect to phi naught, with respect to xy, which direction? It is a kind of three-dimensional view. So let me go back to here. Okay. So now I need to find out. So which So the thing is, see, if I need to find out each position, what is the phase to be compensated? That is phi reflector ray basically. Okay, phi reflector ray.
Okay.
Okay, so here what I'm going to do, see, this is the one. The square boxes are there, right? These are all the
Yes.
boxes where I need to find out what phase I have to introduce in that place, such a way that I can get the planar wavefront. Okay, that is the
Okay.
idea basically. Okay. Now, what I will do, what I'm going to do, see, there is a equation like, for example, you can see here that, see, here there is a Ri term is K naught is phase constant, Ri
Yes.
is nothing but your distance between you can see here,
Yes.
this is the distance, okay. Ri is from the feed point to the location of the ith element or nth element or mnth element, anything. Okay, location of
Okay.
this is the distance. Okay, so
Yes.
and next is you can see here sine theta cos phi, sine theta y sine theta. Why they are giving is that sine phi naught. Why they are giving sine phi naught? Let me tell you one why. So you see here you can see here if you are placing the feed on the z-axis itself, there is no offset in the offset fed. It's a center fed means the phi naught will become 0. Okay, you are
Okay.
going to and you're also expecting the beam to be in the like towards the broad side. Then phi
Okay.
naught will become 0. So you don't have to bother about this offset. I mean this the second terms like let me go to that. So you don't have to bother about these terms basically.
Yes.
These terms sine phi naught and these terms. Okay, you have to only bother about distance between the your horn and the element basically. Why we are multiplying with the k naught? K naught is basically 2 pi by lambda. So let us say Ri is nothing but 2 lambda. Let's say, okay, 2 lambda. So 2 pi by lambda multiplied by 2 lambda. Lambda get cancelled. It will be 4 pi, which means 4 into 180 degree will around 720 degree will be there. Okay, 700 degree phase shift it is introducing in the while traversing from the, for example, let's say is here. So K into Ri means, for example, if it is a center fed reflector or no offset, it's a broadside beam we are considering. So there I don't have phi naught or anything. So I will have only simply K into Ri. Okay, K into Ri.
Okay.
So if Ri is 2 lambda, let's say 2 lambda. Okay, that distance between the where is that figure? Can you go back to that figure?
Go back where, sir?
Yeah, yeah. No, I'm going. I'm going. Yeah. Can you hear me?
Yes, sir. Yes. I'm here. I
Yeah.
can hear you.
So Ri is, for example, why we are multiplying with the K naught because R is, let's say, 2 lambda naught. Okay. Hello.
Okay. Yes,
Okay.
sir.
R is
Okay.
2 lambda. 2 lambda. Okay. So K is what? 2 pi by lambda, right?
Yes.
Multiplied by 2 lambda. So lambda get cancelled. I will get 4 pi. So 4 pi is 720 degree. Okay. So what it does is a sine wave is, traversing like this. If it is, for example, traveling for 2 lambda, it is introducing 720 degree phase shift. So how? Let me show you theoretically. I will explain. This is
Yes.
the sine wave, right?
Yes.
This we call it as 1 lambda naught. Correct? So 1
Yes.
lambda naught corresponds to 360 degree, right?
Yes.
Okay. So if it is quarter lambda, it will be 90 degree. Half lambda means 180 degree, like that. Okay. So if a sine waves travels for 1 lambda distance, which means it introduced 360 degree, correct?
60 degree.
It
Yes.
experienced 360 degree. If it is traveling for 2 lambda, it will be 720 degree. So in order
Certainly.
to represent in terms of phase only, we are multiplying with the K naught here in this equation. Okay. This equation. This equation K naught is multiplied because the distance is known. I want to convert that in terms of phase. This is a propagation constant, right? Phase constant, right? That is why
Yes.
we call it a phase constant. Okay. K naught is the phase constant. Okay. In order to
Yes.
convert the distance traversed into the form in the form of phase, we are multiplying simply you multiply with the K naught. That's all. So
Yes.
these terms are all will come only if you are having considering offset fed reflector and also the or you are considering for the non broadside. See, let me tell you, broadside means what? For example, this is the antenna. If it is radiating in
Yes.
this direction, it is called as broadside. If it is radiating in this direction, it is end fire array. Okay. So if
Yes.
it is a broadside direction, no, broadside direction and also center fed reflector, you don't have to bother about these two terms. Okay, you simply multiply with K into Ri. You calculate the Ri. Ri is what? From the feed point to ith element, the position of the element. What is the distance? Each point. So ideally,
Okay.
what we are doing, we are identifying. See, this is the feed. From feed, what distance each element is. That is what we are finding. Okay. So that
Yes.
accumulated phase, right? That phase we are calculating and then we are introducing in this element so that it get compensated in all the way, in all the elements. See, for example, here we have a 2 lambda, here somewhere and here over here 1 lambda. So which is 360 degree, here 720 degree. We are by introducing this 720 degree over here and also 360 degree over here. Okay, 360 degree over here. What I'm doing, I'm nullifying the all the phase difference between the elements. Phase difference between the elements, I'm going to nullify so that I'm getting uniform phase shift, or we can say planar wavefront. Okay,
Okay. 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 I
that's
understand.
how this works basically.
Oh, that's amazing, sir.
No problem. Yeah,
That's really amazing.
yeah, yeah.
So
Okay.
how
So
can we?
once you now first step is step one is over. Once you
Okay.
find out these phase to be compensated, now
Okay.
you have the things. Next is see phase to be compensated each location Okay. Here what we
Yes.
are having in this plot, what we are having. Let me tell you. My PhD Viva video is there. You can just go through it. There you will understand how the reflector is getting designed. Okay. Hello. Yeah. So now I know like that. So location versus phase. Location versus phase. Location versus phase. Okay. Next step is I am going to analyze the reflector unit cell. Here what I am going to get. This is the phase shift distribution of the aperture. Then I'm going to have element analysis method. Here I'm going to get the element size versus phase, or frequency versus phase. In other terms, it is element size versus phase. Let me show you that. Here you can see here, this is the element size versus phase. Element size versus phase. Let's say element size versus phase. Sorry. Here, let's say, see, I need to be compensated, for example, minus 300 degree. I need to compensate for minus 300 degree at this location. Now I will go and find out which length of the, see, what is the length of the my unit cell, which gives me minus 300. For example, approximately 3. Okay. So I have to put the unit cells of size 3 mm over here. Okay. Let's say this point, I need to compensate minus 400 degree. I have to go back and find out here actually what is common, phase is common. What we have to match this length with the location. That's it. For example, minus 400 degree. So minus 400 degree I'm getting with the length of, for example, 4 mm. So I have to place the element with the length of 4 mm over here. So let's see here. I have to compensate for minus 200 degree. So 200 degree where which length gives me, which is 2 mm. So I have to put here unit cell of size 2 mm. That's it. That way we have to construct the array. First step is what? I have to find out at each point what phase to be compensated. Next point, element design. Then I will get the length versus phase. Okay, so now here what we have to map? Location versus phase here. Here length versus phase. So in both the cases, phase is common. Therefore, you have to map with the element size on the respective location. That's it.
Oh, that's very good. That's very
Yeah.
good. So is the way there is a way to do this one on CST manually or automatically? Okay,
So automatically means you have to take help from MATLAB only. So MATLAB, there is some, I think I can see in online somewhere they mention like that, they can, for example, the unit cell details, right? In this location, this is the phase to be compensated. Then you have to feed that, but somehow some people have done, but you can explore in the net. There is one option available. Or else you have to, initially you can start with the manual one. You construct an array element, each and everything by manually. Then you can, with the help of MATLAB code, you can do that. You have to integrate the, call the CST function in the MATLAB, and then you have to write the size of the unit cell element. So you have to call first you have to design the unit cell element, and then you have to call the particular dimension, whichever dimension you are varying. Then you have to you have to pass the length of the location versus the length, and from the MATLAB to the CST, then that way we can construct the array. I think there are some approaches available, and online also I found somewhere there is a code available. If I find, I will share with you.
Oh, that's amazing, sir. That's really
Yeah.
amazing. So the manually one, can you show me, please? I want
No,
just to
manually
see.
means whatever I have said now, right?
Yeah.
Location is to be compensated, each location I know. Next is, I have to, for example, if I want to compensate in this particular location, minus 400 degree, let's say. Minus 400 degree, what element I have to put? What length of element? Length of the element with the 4 mm I have to put over here, place over here.
Okay.
Similarly, minus 300 degree means I have to put 3 mm sized element. That's like that, you have to place it manually. First, what you
Okay.
have to do is, yeah, you have to only patch, you have to print over here of different size.
Okay.
I think
Okay.
this I have explained in many videos. You can just go through it and then you will understand. No problem.
Oh, okay. Yeah. Yeah, I will check again. I'll check again. Thank you, sir.
Sure, sure.
So sir, the another question is the feeding system. I've
Yeah.
seen in some papers, some people are used different method. For example, some people use on antenna to
Okay.
feed, and
Exactly.
some other people they use plain
Feed
wave,
horn.
yes, to feed, and
Yes.
some other people they use Gaussian wave.
Yes, yes.
So
See, you
yes,
can use anything. You can use feed horn, you can use patch antenna, you can use Gaussian beam, or you can use, exact plane waves, anything. What you are going to, how you are going to validate your array, that is the key here. Okay. You can excite with anything. Ultimately, you have to find out what is the response you have to get for that. That's it. Okay, if you are expecting plane waves, what you will get? You will get the phase distribution on the reflection. While reflection, no, in the reflected beam, right? You will see that
yes,
phase distribution there. That's how we are validating that. Okay, yeah, your array is reflecting with this particular phase. That way you are validating with the plane wave. That's why they are
okay,
using plane wave. Plane wave means it will not have any phase shift, right? Okay, plane wave means it will not have any phase. It will uniform phase. You just impinge on this array and then reflect back. While reflecting back, it will have a phase shift, right? Minus 400 degree, minus 300 degree. If you analyze the phase, a diagram of this particular reflected signal, or reflected fields, you will see the phase. Whatever way you found, right, phase to be compensated at each location. The same thing it will be getting reflected over here.
yeah, okay. So what the particular case of about feeding with on antenna? I've seen in all of most of your video, you
Yeah.
are encouraging people to design a feed antenna from outside
Yes.
and
Yes.
bring it
Yes.
to
Yes.
the
Yes.
array to feed it.
Exactly. Exactly.
So actually, I can show you. Yeah. For example, this I've designed a feed. This one I designed a feed. Uh,
On.
this one antenna. Yes. So,
Yes.
but
Yes. Yes.
I don't know. For example, if I make an array, how can I bring this to the array to excite the array to feed the array?
No issue. See, you can go to modeling,
Yes.
import, sub project. You can
Okay.
import in this array to here, or you can import this onto that environment. That's it. And then
Okay.
you have
Oh,
to position this. That's all. Wherever you want to place. That's all. That is using transform function.
oh, I can
That,
use
for example,
transfer function.
yeah, yeah. You can use transform function. For example, you can see here transform. Sorry, here. Where
Yes.
you want to place, you can place. That's it. But
Oh,
feed tapper, I think last video I have mentioned, right? I think
yes.
somewhere feed tapper means what? What is feed tapper? How it is to be calculated, and how we are going to design synthesis method. I want this much feed tapper. What is should be my on dimension like that? That way you can use those things.
Okay. I'm going again to the video. So,
Yeah, yeah.
so wanna show you uh again about this. This is one of my friends. He has he has designed this array from
Okay,
from from one paper, and
okay.
he has used uh this one, the field source. He has used Gaussian, macro
Yeah,
Gaussian.
you can use. The thing
So
is, the what is the purpose? See, what we are going to do is ultimately what we are going to do. We are going to check my array is, you know, exhibiting the phase distribution that I am expecting. That's all. That is the ultimate aim. You can excite it with anything, but the thing is, it is depends upon the applications. So
yes,
see, Gaussian beam, why we are going? See, in order to mimic some of the antenna characteristics. So you cannot ideally see any spherical waves in nature, right? In any practical antennas, right? So in order to mimic some of the antenna characteristics, I can use this Gaussian beams, which is a customized one. For example, see, if I'm going to use a different feed per se in practice, what I will do,
yeah,
I will get that radiation pattern and then import, and that will be as a far field, feed pattern basically.
Okay.
That's how they designed this. Okay.
So,
So this is
for example, this is the far field what he has got.
okay.
But I don't really see how the face is changing.
Oh, you go to 2D results. 2D results.
Here.
No, 2D. Yeah, yeah. This is the phase change, right? This is a
Oh,
voltage change basically. Okay, you can
okay.
even see in terms of phase as well. Can you go to 2D? Below 2D, there is an arrow, right? Uh, ABS is there, right? On the right, on the right.
ABS.
ABS,
This one?
yeah. That any phase is there? No, no, no. Okay.
No, no, no.
So E
Just only.
field is there. E field is there, right? E field on the
Yeah,
bottom.
E field. E field. This is
Okay,
E field.
okay. No, no, no. Leave it, leave it. Okay. Can you go to 2D? On the bottom, there is an arrow. 2D, 2D.
Okay. 2D.
No, 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 not 2D. No, no. Far field plot. 2D.
Yes.
There is an arrow.
2D.
Down arrow, down arrow, down arrow. Ah, yes, exactly. Oh, okay, okay. It's okay. So go back to 2D results on the left on the navigation tree. 2D, 3D
Okay.
results. On the left, no, 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 here, on the left, bottom. Wherever you have far field
Here.
cuts, right? Far field cuts.
Oh, far
Then
field
next,
cut.
left, come down, left. That navigation. Can you go back to this, wherever you found, where you clicked on this one, far
This
field
one?
pattern, right? No, no, not this one. No, not this one. Come down, please. Come down, left, go left. Yeah,
Here.
here, 2D, 3D results, 2D,
Okay.
3D.
Okay.
Yeah, here. Oh, you're not having. You see, please enable this E field in field monitor. Okay, there you will see phase and everything. Okay,
Okay. Okay.
but you have not enabled the field. Field. Go to field monitor. There is a field monitor, right? On the left. On the left.
Here.
Yeah, yeah.
Field monitor. Yes.
Yes. You can add. Right click and add field monitor. Right click field monitor. Click on the field monitor. Right click. No, right click. New
New field.
field monitor. Yes. Here you can select E field.
New field monitor. It's downloading.
Okay,
It's
okay. It's
loading now.
got hanged. Means hanging. Okay. So
It's
then you
loading.
can select a E field. That's it.
Okay. I can select your
Yeah, yeah.
field from here.
Yeah. Then when you plot that, you see the 2D results, right? 2D, 3D,
Yes.
3D results. There you will see E field. There you can see this one. What do you call phase as well. Okay. Phase and also the what you can say amplitude variation. Everything you can see.
Okay. So maybe I take long more time to understand. Um, what's the difference between using what can affect in terms of result output when we use floquet port or waveguide port, for
Yeah,
example? Because I've seen it.
ideally not much. So Flucket port, why we are going to consider. See, Flucket port, how it works is, it will
Yes.
consider that your unit cell element is there, surrounding by so many unit cell elements are there of same size. You are considering the sort of mutual coupling there. Okay,
Okay.
but but when you are doing this waveguide port, there we are having, you are not considering anything like because it's an isolated element kind of thing. I think in one of my video I explained very clearly that how it is different from each other. You can just go through my PST Viva video. It is pretty much clear. It is explained there.
Okay. I'll go again. I'll watch out because
Yeah,
I'll
please.
watch mostly 90% of the video.
Yeah,
Uh, I'm still I'm still really uh going on. Yes, I've seen the phase distribution, right? The way you showed me last time, just now.
yeah,
So how I can plot the phase distribution.
yeah.
Um, I think most of question you already explained me. So
Yes.
I'm going to start the work right now to if I can find something much better. So I
Yeah.
really
Sure.
thank you for your time. Um,
Yeah.
most of time, if I have some questions, I can be asking you so you can
Please.
make the video. And
Yeah. Yeah.
this it really help many people out there because I'm
Yes.
not alone who's in this trouble. Many people out there they really need such kind of video to
Exactly.
to make progress.
Correct. Correct.
Yeah. For example, is there a way I can add field source manually like this? Something like this.
Which one?
I don't know. Sir, I'm asking. Hello, sir. Do you get me?
Yeah. Yeah. I can get you, but I cannot see the screen on the screen. Hello.
Yes, sir.
Yeah.
I'm asking how we can feed the plane wave, for example, plane wave or Gaussian wave. I don't know how to do this.
Oh, plane wave excitation. Correct.
Yes, sir.
Okay. Okay. Oh, you can so go to field sources. A plane wave. There is one option. Is there right? Right click it. New plane wave. That's it. But it's a kind of tricky. You can get just go to help menu and then watch it. Okay.
Okay, 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 sir.
So here also you can see here that some of the options will be there, but the fill wave thing, it's a kind of tricky thing. But you will see in the some of the help menu, you will get it. No problem. Don't worry. Okay. Yeah.
Okay.
Yeah.
So, is there? Do you think it's very good idea to export far field,
Yes. 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 Yes.
like
See, that
into?
will be easy. Actually, there is an option called you can just export the feed far field pattern and then use
Okay.
as this one
Yeah,
feed
I can use
basically.
it. I can use far field
Yeah,
as
exactly.
a source.
Exactly. Exactly.
Oh, I think that will be easy for time saving.
Yes, yes, yes.
Oh,
Exactly, exactly.
oh, that's amazing. So, what about uh the array port? How we can assign the port in array? Is it same method we use for unit cell?
Yes, exactly, exactly. Same.
Okay.
Because you are going to fix the feed, right? Feed
Yes.
pattern, right? Accordingly,
Yes.
this will be illuminated basically.
Okay. Okay. I see. I see. That's really good. Um. So maybe the last question. Sorry.
Yeah,
Um. Do you think using MATLAB to automatically design unit cell or reflector array, is it very
yeah.
good compared to direct using CST?
Yeah. See, you can analyze, but in the thing is, if you understand everything clear, then it is very easy to use MATLAB. But to start with, you can go see initially start with you can go for CST and then you understand things, stuff, and like that. Then you can go back to this one anytime. Okay.
Okay, okay, okay.
Yeah.
Oh,
Okay,
okay,
that's
okay.
it. First, you need to understand the things how it works. Then you can play with anything. Yes.
Okay. So if I want to understand again about the size of unit cell, you mean most of the case is lambda by 2 in
Yeah.
general.
Yes. Exactly.
Okay. So we can also optimize it by lambda by 4 or something like that.
Yes.
Oh, that's
So
fine.
but lambda by 2 is the commonly used one. Yeah.
Yes.
You can start with that, then you can, tune it. That's it.
Okay. Thank you so much, sir.
Yeah,
Thank you
yeah.
so much.
Okay.
Um, I think I have really get most of questions I have today.
Yeah.
It's going really to help me to. So maybe the last question I just remember. Do
Yeah.
you have idea what about micro? Is it micro? Yes. Because I've seen some people saying that we can make phase distribution using macro. Is it that correct?
Yeah, but I have never used, but there is an option. Yes, macro as well.
Okay, okay. Because I've seen some people discuss on the group
See,
that we
now,
can.
yeah. Now many options are there now. Yeah, you can explore that. No, first if you please understand this everything, then you can
Yes.
just, yeah.
All right. All right. So thank you so much, sir. Thank you for your time.
Welcome,
I know
welcome.
it's quite late. It's quite late over there.
Yeah, it's
Uh,
okay. No.
you really
Yeah,
managed to give me a few time to encourage all the research community. Thank you so much
yeah.
for your time, sir. We are
Yeah,
really we appreciate your efforts what you are doing, sir.
thank you so much. Yeah, welcome. So have a great day. Bye bye.
Thank you
Yeah.
so much. Bye bye.
Bye.
Thank you.